My name is Nathan Nelson. I'm a professor here at Kansas State University, and it's my pleasure today to present some research that we've been working on related to phosphorus management and cover crop systems here in Kansas. I want to thank my co-authors, Elliot Carver, Peter Tomlinson, Craig Rosenbaum, Gerard Klutenberg, and Deanne Presley for their contributions to the research that I'll be presenting here today. Runoff from agricultural fields can remove topsoil and plant nutrients. This obviously represents a loss in productivity for the field, but the sediment and nutrients that are lost can accumulate downstream and cause additional damage. Sediment accumulation decreases water storage and interferes with navigation in lakes and rivers, which can result in costly dredging operations. Sediment also harms the aquatic environment, destroys fish habitat, and decreases the recreational value of the water. Just as nutrients increase crop growth when added to soils, these same nutrients increase algal growth in aquatic ecosystems. The algal blooms can also degrade fish habitat and interfere with recreation. Over the past decade, we've actually seen an increase in the number of harmful algal blooms, or algal blooms that release toxins. Here are a few recent headlines related to sediment issues in water bodies here in Minnesota, including a $16 million price tag for dredging in the St. Louis River. And then here are a few examples of recent headlines related to algal blooms in Minnesota lakes. Although there are multiple causes for these algal blooms, or multiple factors that come together to create the optimal environment for an algal bloom, reducing nutrients or nutrient inputs is an important tool we have to control these algal blooms, right? So just like in production fields, we want to create optimal environment for crop growth, and so we add nutrients to make sure that when everything else is perfect, nutrients are not limited. Well, in an aquatic ecosystem, we kind of want to do the opposite. When everything else is optimal, we'd like those nutrients to be limiting so that there's not a bloom. But in this case, those nutrients are not limiting, right? As shown here, nitrogen and phosphorus inputs to water bodies generally increase algal growth, especially when they're added together. For the remainder of my presentation, I'll be focusing on how our management practices impact phosphorus losses. However, I fully acknowledge that controlling nitrogen losses are also an important part of the equation. There have been many studies that have talked about how cover crops can reduce erosion. A few studies talk about runoff and reducing phosphorus losses, but a lot of these studies up until recently had all been conducted in conventional till agriculture. And we had a fair number of producers come to us who were no-till producers, and they wanted to use cover crops as a best management practice, particularly when they were going to be fall broadcasting phosphorus fertilizer. Now we have a lot of previous research that shows that subsurface placement is really the best method from an environmental standpoint. However, there are economic and management benefits from a surface broadcast fertilizer, and we couldn't find any data on how cover crops impacted phosphorus loss in no-till systems, much less how the cover crops would impact phosphorus loss from different fertilizer management systems in no-till. So we went ahead and designed a research study to respond to these questions. Overall, we wanted to know how cover crops impacted the right placement and timing of phosphorus fertilizer. Particularly, are cover crops going to reduce phosphorus loss from surface broadcast fertilizer in no-till? And we also wanted to look at how phosphorus fertilizer impacts a placement and timing strategy. So a lot of our previous research looked at phosphorus fertilizer applications in different placements, but at the same time generally in spring. And a lot of our producers, if they're going to broadcast fertilizer, they would do that in the fall. And so we wanted to compare that, the typical management practices that our producers would be choosing between. So in order to do this, we set up the Kansas Agricultural Watershed Field Laboratory, shown here. So we took a field with a fairly uniform slope of about 7-8% that had parallel terraces running across it, and divided up into 18 small experimental units. Here's an aerial photograph of this study, and you can see the parallel terraces moving across. The field is sloping from the top of the photograph to the bottom. And what we did is we inserted a waterway in the center, added some berms, and divided this into, like I say, 18 plots about 1.2 acres in size. Here's a photograph looking up again, just giving you up the slope there in the middle waterway, giving you a little bit different perspective of what this study looks like. And you can see some of the equipment we used to collect the water exiting the plots. So we established this in 2014. Our first cropping year was 2015. It had been managed as a conventional till field prior to that, so this 2015 is a conversion from no-till to, or from conventional till to no-till. It's also that first year of cover crop growth. And so I'm going to present you data from 2016 through 2019, right? So ignoring that first year, which was a little bit of an oddball. But we did have our treatments in place that year, right? Cover crop and fertilizer management. We have 3 different fertilizer management treatments. Control, no phosphorus fertilizer application, and then a fall broadcast treatment or a spring injected treatment. That spring injected is a 2x2 application with a planter. And both of these are about a little over 62 kilograms per hectare, a little over about 55 pounds of P2O5 per acre was the application rate. Then each one of those 3 treatments was present without a cover crop or with a cover crop, and that cover crop changed throughout the study based on the weather conditions and the timing. We had winter wheat and triticale, mainly a small grain is what survived the winter, and we had rapeseed a few years. So at the edge of each plot we collected all the runoff with an H flume, and then collected samples for every single runoff event, samples of runoff water, analyzed that for sediment, total phosphorus, and dissolved phosphorus. So we can look at concentrations and then also the total losses, and that's what I'll primarily be presenting today. I'll present a little bit of yield data and some soil test data just to give you some background on how these treatments influenced some of our more typical agronomic type responses. Throughout the study we had 4 years of data, 2 years that had fairly wet years with high precipitation or precipitation above normal for us, and then a few years with lower precipitation, right? And so you'll see 2016 and 2019, those were a little above average. That 2019 was extremely above average and had a very, very, very wet spring that year, which obviously is going to impact runoff. 2017 and 2018 were a little bit drier. These figures here show the treatment impacts on soil chemical properties. The primary impact of the phosphorus fertilizer treatment was an increase in soil test P concentrations at the surface, or at the 0 to 2 inch depth, right? The increase in soil test P was about the same for both the surface broadcast and the spring injected treatments. Notice that there was quite a bit of stratification by the end of the study in 2019, right, where the soil test phosphorus at the 0 to 5 inch or 0 to 2 inch depth was about 70 parts per million, where at 2 to 6 inches we're below 10 part per million. What this results in is about a 25 to 30 part per million soil test P for a 0 to 6 inch sample. Okay. The cover crop treatments increased total carbon and total nitrogen by the end of the study, and so that's what's shown in these graphs on the right. This is at the end of the study, and here we took samples at a little bit finer scale, so 0 to 1 inch, 1 to 2 inch, and then 2 to 6 inch depths. And at the very near surface we have higher total carbon, higher total nitrogen in the study. No impact on soil test phosphorus in the very near surface. If you get down to the 1 to 2 inch depth, there was a slight decrease in soil test phosphorus where there was a cover crop, but not any substantial impacts on soil test phosphorus, not nearly like what we see from the fertilizer treatment. So the main treatment impacts on phosphorus were from the fertilizer management. Now I'll show a few slides looking at yield and I'm not going to get into all the details here. So we see that over the 4 years, an average increase of about 10% in relative yield with phosphorus fertilizer application. Statistical analysis indicated that there was not really any interaction between the phosphorus fertilization and the cover crop treatments, meaning that the fertilizer effect was about the same for both cover crop and non-cover crop treatments. And I'll show you that here in this additional graph where it splits apart the fertilizer effect for no cover and cover crop, and we see basically the same response. And like I say, that statistically we conclude that the response is the same, an increase in yield for both cover crop, or for fertilizer treatments in both cover crop and no cover crop, even though the yield was a little bit less, right, in the cover crop treatment. And that really came because of a few particular years, right? In 2017 and 2018 we saw lower yields on average with cover crop. The big statistical significance there was in 2017, right? That was the 1 year where we saw a big yield drop with the cover crop treatment. So just based off of yield, we would say there's a slight yield loss from cover crops over the course of the study, and we see in general an increase in yield with fertilizer application, but we don't see a difference in yield between the two different methods of fertilizer application, fall broadcast or spring injected. However, we'll see that these treatments have substantial impacts on water quality. At the outset of the project, we would have expected, or we did expect, that cover crops would have decreased runoff volume, but that generally was not the case. And so here we see runoff volume averaged over 3 years, 2016 through 2018, and there was no impact of cover crop on runoff volume. But during those same 3 years, we see a substantial impact on runoff intensity, where the cover crop decreased the peak flow rate on average by 27% for each runoff event. We saw a tendency for an increase of about 5 minutes for the time to runoff initiation. This was very close to statistically significant, p-value of 0.057. We saw a significant increase in the time to peak. So the peak runoff in the cover crop plots occurred about 7 minutes after the peak runoff in the no cover plots. And then we saw a tendency for longer runoff, right? So about a 45-minute increase in runoff duration during the study. So although we didn't have an impact on the total runoff volume, we're impacting how the runoff leaves. It's slower, right? Less intense runoff events. And so less intense runoff events, they're shown here in this figure. Shows the hydrograph for two plots. These two hydrographs have actually the exact same volume of runoff, but you can see it's a different pattern, right? Lower peak and a broader peak. Now in 2019 we actually did see a significant impact on runoff volume, right? So a decrease in runoff volume in 2019 with the cover crop. This decreased runoff intensity resulted in decreased erosion every single year of the study. 60 to 70% decreased in erosion. Even in the very dry years, we still decreased erosion every single event, pretty much. Again, this is related back to that decreased runoff intensity. In 2019, this change in runoff intensity actually influenced also residue loss, and it's pretty hard to quantify this. And so I've got some photos here showing early in the year where the no cover crop plots lost a lot of crop residue from the prior years, right? So this residue would have protected the soil from raindrop impact, but instead we ended up with a fairly bare-looking no-till field without much residue. And then throughout the rest of the year, this soil is exposed to raindrop impact and surface crusting. And although I don't have data on exactly why we had less runoff that year, I feel that this surface crusting, or this more bare soil and probability of greater surface crusting probably contributed to that lower runoff in that year. Now, generally with lower erosion, right, 60 to 70% less erosion, we would have expected lower phosphorus concentrations in that runoff, right? But instead we saw that total phosphorus concentrations were about the same for 2 years, and then 1 year we had an increase in total phosphorus concentration in 2018, then 2019 a decrease. So we didn't have any consistent effect of cover crop on total phosphorus concentration in the runoff water. What we did have was a consistent effect of cover crop on dissolved reactive phosphorus concentrations, about a 70% increase in the dissolved reactive phosphorus concentration in the runoff water. Now, dissolved reactive phosphorus is like it sounds, it's dissolved in the water, so it's not attached to sediment. This is also generally more highly bioavailable, right? And so by increasing dissolved reactive phosphorus, we're potentially increasing the availability of this phosphorus to aquatic plants and algae, which could potentially even make algal blooms worse by having more bioavailable phosphorus. Now, these are concentrations in the runoff water. Here's a slide that shows the cover crop effects on the total loss of dissolved reactive phosphorus and total phosphorus. We see that the total losses of dissolved reactive phosphorus were a little bit larger when we had a cover crop in 2016, 2017, and 2018. and 2019, although we had higher dissolved reactive phosphorus concentrations with a cover crop, the loss was about the same. This is due to that decrease in runoff volume in 2019, right? If we look at total phosphorus losses, again, 2016, 2017, no effect of cover crop on total phosphorus loss. 2018, slight increase in total phosphorus loss. This is related to that increase in dissolved reactive phosphorus and occurred during a year where we had very low erosion, so most of our phosphorus loss was dissolved that year. 2019, the cover crop decreased total phosphorus loss, and again, this is related to that high sediment loss that year, right? And so we did have a significant decrease in total phosphorus loss that year. Cover crops do a pretty good job of reducing runoff intensity and an excellent job of reducing erosion, but they're not a silver bullet. That's what I'm taking from this, right? Their effects on phosphorus loss are mixed. We're seeing some increases in dissolved phosphorus, mixed results on total phosphorus loss. So we really need to look at other methods to control phosphorus losses. We can't rely on cover crops to do everything. And that's really what we see from our fertilizer treatments in this study. Now, in general, we saw that cover crops had the exact same impact regardless of fertilization strategy, and fertilizer treatments had about the same impact on phosphorus loss regardless of cover crop treatment. This data here shows the dissolved reactive phosphorus and total phosphorus concentrations in runoff. We see that by subsurface placing that fertilizer in the spring, with the spring injected treatment, we saw consistently lower dissolved reactive phosphorus concentrations in runoff every single year of the study, about 41% decrease of dissolved reactive phosphorus concentration. The total phosphorus concentrations decreased by an average of 29%. This was a little bit mixed from one year to the next as far as whether it was significant or not within the individual year. But over the entire study, we did find a statistically significant main effect where spring injected had lower total phosphorus concentrations. This is mainly due to the decrease in dissolved reactive phosphorus, right? That's where the fertilizer treatment really impacts phosphorus concentrations and loss. Based on the year, we saw a 5 to 50% decrease in dissolved reactive phosphorus losses with subsurface placement compared to fall broadcast. The 1 year where we didn't see any impact, that was 2018. That was a drought year where we didn't have any runoff from October until August, right? And so during those critical months, those spring months where we would expect our treatments to have a big impact, we just didn't have any runoff. For total phosphorus, again, about the same thing, just a little bit less of a reduction. 0 to 34%. Significant reductions happened in 2016 and 2017. There was a tendency in 2019 for that reduction, but a lot of variability in total phosphorus loss makes it hard to detect those differences. Overall, had about a 16% reduction in total phosphorus and 33% reduction in dissolved reactive phosphorus. So kind of in summary, our cover crop decreased our runoff intensity, increased sediment and particulate phosphorus loss, and increased dissolved reactive P loss. And the reasons for that increase in dissolved reactive P loss are we're not certain about. We have some, there's some possible reasons. It could be coming from the cover crop residue, but I think it's got to be a little bit more than that. I think that this decrease in intensity may be increasing the interaction between runoff and soil in the field. Maybe increasing the release of phosphorus, or the time of reaction increases the amount of phosphorus that actually gets desorbed from our soil. We also have less sediment loss, and so less sediment mixing. So just the fact that we have less sediment in our sample means that there's less of a chance for phosphorus to adsorb to sediment in transport. So there are a few different things that could be going on here. But we see an increase in dissolved reactive phosphorus concentration and loss with a cover crop. And the variable effect on total phosphorus really depends upon the year. If we have high erosion years, right, then we start to see more of an impact. That 1 year where we had really high erosion, we had more of an impact on total phosphorus. And there we decreased total phosphorus loss with cover crop. We found that subsurface phosphorus fertilizer placement consistently decreased dissolved reactive phosphorus concentration throughout the study. Decreased dissolved reactive phosphorus loss in 3 out of 4 years, and total phosphorus loss was decreased about half the time. So we're still going to conclude that subsurface phosphorus placement is an important best management practice, even when you're working with cover crop systems. It's still important from an environmental standpoint to follow the 4 R's and subsurface place that phosphorus fertilizer. I want to say thanks to and acknowledge our larger team. A lot of people worked to collect this data, and I appreciate all of their assistance. Also want to say thanks to our funding sources. We've had a variety of funding sources: the 4R Research Fund, the Foundation for Food and Agricultural Research, Natural Resource Conservation Service, Corn Commission, Soybean Commission, National Institute of Food and Agriculture. All helped to support this work.